So, like I mentioned, we'll go over section 40 today. I'm kind of skipping over section 39 because essentially it's just talking about what a pipeline is. I'll just very briefly say it since it is part of like it. Well, okay. A pipeline basically, the idea of it is that you kind of have a procedure that goes forward to do like your machine learning parts. So you might do something like scaling or like PCA, and then actually feed that into saying a specific machine learning algorithm itself. So that can also be done with grid search. So grid search is really useful in the sense of basically grid search is literally just trying like a bunch of different methods and different parameters for a machine learning algorithm and seeing how well they perform. So you can actually tie those in really well. Scikit-learn, it has a really good set of API basically to allow you to create this pipeline. It's also nice because then it means that you can like use the same process over and over again without having to like really code it out completely yourself. Basically automates the whole thing for you. So that's kind of like realistically what you do, especially when we get into something like this, where we're talking about section 40 about big data. And so sometimes you might have not just all the calculation, all the algorithms being done on one machine, you might have it on multiple machines. And so it's useful to actually pass around the pipeline to let that basically, what's it called? Essentially like crunch the numbers on multiple machines and then aggregate them together. So that can be really useful. And so we're going to mostly focus on section 40. So intro to big data. So I'm going to go ahead and start sharing my screen. And let's get this going. And again, this notebook is on the repo that I have for all the different sections and everything like that. So there's not too much in here. There is some code that will maybe reach at the very end, but for the most part, it's mostly instructional. So I think in the curriculum itself, section 40 is centered mostly around PySpark. I'm going to talk about like, in general, like what big data is, and like when we talk about, big data, which is like this big, hot term right now. Like what are we talking about? What do we mean by a distributed system? What do we talk about a parallel system? And one of those ways we can interact with it is something with Spark. And then for us, we're going to use PySpark since Python. But I'm just going to talk about that general part. So big data is kind of, you hear this term probably thrown around a lot. And so it's important to know like what we mean by big data. And so big data really comes from the fact that it's just a different amount, meaning a different kind. So like in the old days, and old days could be like, 15 years ago even, but like not too long ago, we had data where like, okay, we have a large set of data, but not so large that we couldn't put on one machine. But now we commonly have huge amounts of information, huge amounts of data, maybe in a database or data set where one computer cannot crunch all the numbers. And this is actually really important because pandas, which is what we've been using pretty much for this whole course, typically can't do, it has to be loaded into memory on that machine. So you can think of it, if you have 12 gigabytes of RAM on your computer, when Pandas loads in the data, it has to basically perform on that 12 gigabytes of RAM. You can kind of circumvent this by basically getting really powerful computers. Like you can have desktops with like 128 gigabytes of RAM. That's not too uncommon for like a desktop data science specific computer. And you can still do like many things with that one computer. But sometimes it's just so much different. Like there's so much data. That's one form of big data. There's so much data that you can't really work on it on one computer. You have to distribute it out. So one thing to note is that there isn't a clear definition of like what is quote unquote big data, but there's kind of like a general consensus of like what this is. And essentially it comes down to you can't do it on one machine. Okay, so I'm going to talk about the numbers everyone should know. And that's like a actual thing, like you could search for numbers everyone should know. And basically it comes down to the fact of like, when we're talking about big data, what things we should consider. So there are different parts of the computer itself. So depending how technology, how technical you are, you might know this, you might not know some of it, but basically the main parts of the computer and processing, it goes from the CPU, the memory, which is like RAM, storage, which sometimes we'll talk about as memory, but think of like storage, like, keeping things away, and then using the network itself, which is interconnecting amongst different computers like the internet, right? So we usually talk about the CPU as being like the brain. And so the CPU basically is the thing that actually does all the computation. Everything else essentially is giving stuff to the CPU to do things. And this time right here, this 0.5 nanoseconds, this is approximate, like just to give you a scale, is basically how long it takes things to actually run on the CPU. So basically, you can do things very, very quickly on the CPU. It's the fastest part of the computer, and you can think of it as the brain. The next part we have is like the memory or RAM. It's usually, you can think of it like short-term memory. And so it's much slower than the CPU, but still relatively faster, or fast compared to the other parts we'll talk about. And so essentially the RAM itself is going to be feeding in information to the CPU to actually do work with. And then the CPU will pass it back to the RAM, the memory, and keep that for a short time before it can read it off into what we call like read it to disk or read it to storage. That leads us to our next part, which is storage. And usually nowadays are like SSDs, but hard drives and stuff like that. And this is kind of considered more like long-term memory. So things, like you store a bunch of photos or videos or files or whatever you have on your computer, that's where most of the information sits. And to read and write from this disk, from storage, is much slower than memory. Basically takes a lot longer. The real reason some people sometimes ask, like, can't we just like put everything on memory, like in RAM, since it's like super fast? And that's what you'll do when your computer's on. But when the computer turns off, or if it loses power at any point, this is short-term in the sense that literally it won't be able to keep the memory on there. So basically anything that's stored on RAM, if you turn off your computer, basically it'll just disappear. So that's why we need this long-term storage, stuff like that. Especially, it tends to be cheaper as well, okay? And then our last part is basically our network. And our network is basically just connecting different machines. And this will be important, for the most part, like we usually only care about these parts when we're working on our local machines, but network will become really important when you start talking about distributed and parallel systems, because sometimes it makes sense to divvy up the work between different parts, different computers, and you can use the network to pass information back. But sometimes it's actually going to be slower than you'd expect. So it's important to understand that network is going to be our slowest aspect here compared to storage, memory, and CPU. Okay, and I think this is actually something that came up. I had to like dig a little bit to see where this came from exactly, like where it's referenced. There's actually a blog here that where this kind of came with the numbers you should know and getting this idea of what's going on. Of course, these numbers will change as well, but generally the CPU will be fastest, memory, storage, network. Those will always, like, unless we have some drastic change in like on how we do computers, these are pretty much consistent. It's just setting how fast. And it was kind of fun. There's this little interactive graph here that you can actually adjust to say what kind of, what year it is. And you can see how fast everything goes. And you can actually see, is that based on the CPU versus, RAM versus storage, you can actually get an idea of that this is always going to be a certain speed and a certain, so how fast things are from each other. Okay. So this is when it's like, okay, cool. Like, let's kind of figure out like why these parts are important. And I think this is a little important part with like understanding how computers actually function. When you do something on your computer, what is it actually doing? So we're going to ignore network for right now and we'll talk about just storage, memory, and CPU. So if you imagine like if you have something on storage, so imagine you have a file, like a CSV file. So I'll put like CSV here. This is like where your storage is, your hard drive or SSD, right? And right here, we'll call this like the memory stick right here. This is our RAM. And essentially what happens, I kind of like personify these guys, and I'll put CPU as this round thing right here. Put CPU. And essentially what's going to happen is that if I want to take this CSV, basically the RAM stick right here is going to grab the CSV and try to load it into here, which is going to take some time. So it takes some time for it to load. And then once it loads in here, it's going to say, okay, let me go ahead and pass it off to the CPU, and that's going to take some time to go through. And then the CPU is pretty much going to like work on this really quickly, and it's going to hopefully get some pretty good results. And then what it'll do, it'll actually take this results and pass it off to the RAM stick, right? Which again takes some time because it has to read it in. And then it's going to take even a longer time for it to pass out some new stuff to the hard disk. So if we actually want to save things, okay? So for the most part, you want to keep everything on RAM. So the thing is here is something called thrashing. So sometimes what happens, and this, I don't know if you've ever like opened up like Activity Monitor, or for Windows or something similar, like I can't remember what it's called now, but basically some kind of performance application. And what you'll see is that if you start using your computer, you'll see this weird thing where your CPU usage will go way down, and then RAM is like way up. So like you're using like all the RAM you possibly can. Let's say you have like an 8 GB memory on your computer, and it's using it like 100%, but your CPU usage is like almost like 1 or 2%. And what's happening here is that the CPU is working, there's so much information to pass from RAM to CPU that it's taking forever for the RAM to actually pass over that information to the CPU. So essentially what happens, the CPU is like twiddling their thumbs, just waiting and waiting and waiting for something to actually happen. And essentially it's because the RAM and the hard drive can't feed the CPU quick enough. Essentially you have too much data for it to try to chomp through. So this is something called thrashing. And this is actually kind of a big deal because like, oh, it basically means a bunch of wasted time for the CPU waiting for information to crunch. If we could speed that up, if we could maybe feed the CPU more efficiently, then we wouldn't have that issue. And this is actually where we start looking at other systems besides just a single local computer. Okay. So sound good so far?
Yeah, all makes sense.
Okay, cool. So not sure if that was something you knew or didn't. Oops. Let me get rid of there. There we go. Oh my gosh. Gotta get back my mouse tool. Okay, cool. So this kind of comes down to like, okay, like how do we identify data, big data? And so usually there's kind of these three V's of data. I think there's a fourth V that sometimes people talk about, but the main ones we really think about are volume, large amounts of data, velocity, how quickly is this data actually generated, and variety, is it structured or not? So we say big data is any one of these three V's, possibly even more. And when it makes more sense to split up the work into multiple computers, but basically using the slowest part of the network and splitting it up and to work on a parallel or distributed system. Kind of quickly going through these three V's though. Volume is pretty obvious. It's like if you have a large amount of data that you can't keep on your computer, that's going to be big data. And by keep on your own computer, that could be simply saying, I have 100 gigabytes of data and I can't fit that all on memory. Basically, if you try to load 100 gigabyte CSV, which can exist, you can try to load that onto your computer's memory, but it's not going to be able to fit. And basically, you're not going to be able to load a pandas data frame or whatnot. And essentially, your computer's just going to get stuck, even though the CPU is doing absolutely nothing. The other part is velocity. So if basically data is coming in very, very quickly, so a lot of like modern, like think of like financial transactions and stuff like this, where data is being generated very, very quickly. It's happening very, very quick going through. You can think of like Twitter, you can think of a lot of websites, stuff like that, is that your computer has to move fast enough to keep up with all of that data coming in. And the thing is that most computers, you know, depending on the size of the website, really can't handle all that. So you have to distribute out that workload. So that way you can actually keep up with the data coming in. Otherwise, it's going to be too old by the time you're actually done computing on it. Okay. And the third part is variety, which is a little subtle. So you might have heard a term called a data warehouse. I don't know if you've heard that before, but data warehouse is kind of like this. You can think of almost like, you know, keeping data like in your nice database. It's all neat and structured and everything like that. Well, there's this kind of new concept called a data lake. And essentially a data lake is more or less basically just pouring in all the information. Could be pictures, could be audio files, it could be, you know, different formatted text. And basically you put it all within there. And essentially it's this huge mass of storage and you have to pull that part out. Well, it's really difficult to pull that out correctly and consistently to make sure it works out well. So variety is actually a big part where if you have many different types of data that are unstructured, you have to have something to clean that up essentially to pass it on to actually do something interesting. And that's where distributed systems also work really well. Okay. So this is kind of the motivation of like what big data is, the different parts, and the network part is essentially our slowest part, which is what encourages when to actually distributed systems. So that'll lead us to here. So note that I'll say like parallel and distributed, and those are two different things. So the first thing is a distributed system. So you can think of distributed basically just means that you take up a task or take up a task and you split them up and they're executed by different workers. And your worker essentially usually is like a CPU. So you can think of when you do distributed systems, each you have multiple CPUs, basically multiple brains, and each brain has their own memory. So that way they're not waiting for one memory stick to feed multiple CPUs. Usually we think of these like CPUs as being sharing on a network, and essentially they're passing through messages and stuff. So you can see here basically a more server-based network where you have one main computer and it's split off to different parts. You can also have a peer-to-peer network where essentially you have the different CPUs communicating all directly with each other. Both of these could be distributed systems itself. Now, Yeah, go ahead.
Sorry. So these are all connected by network, so you're going to see the biggest lag. So like you pass it off to separate CPUs to do all of like the hard computational stuff, but you would see a lag from the CPU back to the
Mhm.
main. Okay.
That's right. Yeah. And you can think of it like you want to feed the CPU data. Like the CPU can crunch things really quickly. So if the CPU is waiting because it's just waiting on the network going forever, then that's probably a bad system.
Mm.
But the opposite, like we talked about with thrashing, could be is that there's too much data to process all at once that the CPU is waiting for so long for this data to be moved from storage off to memory back to the CPU and then back to memory and then onto storage and getting the next part. So that can actually be really slow. I actually have a really good analogy, I think, of this because back when I was a teacher, we would have to grade assignments. And there's a way, one thing we have, I remember there's a certain time of the year where basically we have standardized tests, and it was a relatively small school. And we had to like basically distribute out different tests and stuff like that to the different teachers and stuff like that. And we essentially had to combine it all together in alphabetical order. And what's kind of cool is like there's this really nifty way to organize. Basically, you take the stack and split them into different parts and say, all right, you organize this stack, you organize this stack, and you organize this stack, and put in alphabetical order. And so each person can put the alphabetical order and then combine them later on. So that's kind of a distributed way. So it's nicer because if you imagine had like 500 tests and trying to like organize it alphabetically, it would take a long time. But if you can split that test, into like, let's say 20 different tests for different people, and you organize 20 tests alphabetical order and then combine them later on, that's actually really fast. Now, this is where it's kind of like which is faster. So if you had like 500 tests, let's say in the principal's office, and you could either have the one principal trying to organize those 500 tests, and like that's kind of like one CPU. Another thing you could do is you can split up the data and pass it on to multiple, teachers, right? So maybe you split it up into like 10 piles and give it to 10 different teachers. Well, the network in that way is kind of like you like literally grabbing the papers and passing it off to each classroom, for them to organize. So if it takes you a long time for you to give out all this information, it might not be worth it. So if you imagine if you gave like, let's say instead of like 20 or 50 papers, you gave them like 2 papers to say, oh, here, I'm giving you 2 papers to organize in alphabetical order, and you were to give that out separately, that's going to happen very quickly for each classroom, but it's going to take you so much time to actually go walk over and collect everything. And that's essentially that balance. Mm-hmm.
Is this similar to the like traveling mailman or traveling salesman problem? It's like
Not so much that. It's more like direct in that case. Traveling salesman is like trying to find the most optimal way. This is much more like, oh, let me just like, if I can give it out to each person, but if it takes like a minute to pass through and then process this data and then
you're
pass it
okay
out
with that. Okay.
Yeah. So one way you can think of this is like imagine your network takes like a minute no matter what you pass through. So it takes a minute for you to just pass information back. And so let's say you can give like a 10 gigabyte file within a minute to this one computer. That one computer then can crunch that 10 gigabyte file. And by the time it's done with that 10 gigabyte file, you can start passing it a new set of files. So you can kind of keep feeding that beast.
Yeah.
The opposite, a bad way. Oh, yeah, sorry, good.
When you're doing the server-based network, would you be like, so for example, for like the A to Z stack of papers, would you give someone a chunk from A to C? Like, would you sort it first, or does it not matter? Like, does computational speed not matter?
Yeah, it turns out in this scenario, you can actually give them unordered papers and say, here's just a random set of 20 papers, and you set another 20. And then basically what happens at the end is like, okay, they have it organized. Each classroom has it organized, their personal stack from alphabetical order. You can take those stacks and then combine it yourself. And it's much easier to do that versus trying to combine the original like 100 papers yourself.
Okay. Okay.
And I'm kind of like leading into a bit of like okay, this is what you can kind of do. It's, if you're curious, it's called merge sort.
Okay.
To kind of like split this up in a certain way and be able to like have, yeah, it actually works really well in the real world. Like I tell every
I feel
teacher,
like I have, yeah, like I remember this from like a freshman year.
Mhm.
We were talking about like computational speeds and like why, because it was like figuring out how to like sort an array in Java, and like why you couldn't just do it a certain way, and like trying to figure out what the fastest, like the P set was to like come up with the fastest way, and the answer I think was this algorithm.
Yeah, there's some interesting ones. Like, I won't go too far into it, but basically there are some interesting algorithms that can say how quickly you can split it up. But merge sort in particular is really interesting because they work really well for parallel systems.
Okay.
So essentially what you can do, you can split up the work and say, okay, you will go ahead and sort this small little pile. And you sort this small little pile. And then to combine them is actually really easy. Merge sort, if you're like talking about sorting algorithms, is really interesting because basically the way it functions, it will always, if you know how big your pile is, you can guarantee how much time it's going to take. It might not be the fastest, but it'll be relatively fast, and you'll always know the same amount of time. The problem is with merge sort is that if like things are already sorted or mostly sorted, it's still going to take you the same amount of time if they were completely random.
Got it.
Yeah. So anyway, but the main reason why we talk about this is that you can split up this work, and the whole point is like, do you give them bigger chunks and let them process it through and then take that time to pass it back through the network? Or do you give them smaller chunks because your network's relatively fast? If you imagine, like I said, like those two papers, like if it takes them really quickly to go and they're just waiting for the next set of papers or waiting for it to pass it back, it's not a very efficient system.
Okay.
Cool. Yeah, that's my long-winded analogy, I think.
Sorry.
No,
I think I also got us off topic.
No, that's all right. No, that's actually a great example of like ways we can do stuff. But yeah. Anyway, so that is distributed systems. Essentially, there's some system that's passing it out to do the next part. Sequential systems is basically kind of like a really simple, I don't even have a diagram for this. These are actually come from the curriculum itself. But a sequential system basically is saying you start with the one thing and you go to the next thing and go to the next thing and go to the next thing. So you can kind of imagine, I'm trying to think of a good scenario, but like if you imagine like you have a stack of papers as a teacher and you only grade question number one, you grade question number one, and then you have to pass it to the next person and they grade question number two. And then you pass it to the next person and they grade question number three. So you have to wait each time. Some cases, that's the only possible way for you to actually process it. One way you can imagine this is like maybe doing some math, for example. It's like you have to add two numbers together before you can multiply them together. It has to be sequential. But sometimes you can do things that are like what they call like embarrassingly parallelizable, where essentially it's like, well, you don't have to wait for the first person to finish. You can like do different steps waiting for that next person and then combine them at the very end. So you can imagine like just passing papers and say, all right, whenever you're done with question one, just go ahead and pass this to the next person and they'll grade question number two and so on. So you don't necessarily have to wait in that order. So that's kind of like sequential is kind of like the opposite of our distributed. And this kind of leads us into, sequential is like kind of the opposite of like parallel. So parallel and distributed sometimes get confused because they usually are used together. But parallel just means that you're executing different tasks in a non-sequential order. So you can do things out of order, essentially. And so multiple CPUs are sharing the same memory to communicate itself. So this is, again, from the actual curriculum, is that here's a traditional sequential processing. So basically you do step one, and then you pass on to step two, and then pass to step three, step four, and then it goes into the CPU. But in here, you can imagine doing multiple steps for each kind of like brain going off here. And then it passes off to the same CPU and connect it together. So parallel processing is that basically it's like everyone is doing it together in parallel. So
sorry, I'm not sure I follow. So is it that each individual CPU is like the top one's doing step one, second one's doing step two, third one from the bottom, step three, step four, etc.?
This might not be the best too. I don't like this picture perfectly, but it's more like if, let's say for parallel processing, it's like here, I'm going to give you a stack of papers and you go ahead and start just like, it's not even about better. I'm trying to give a good example of this, but you can think of it as like, you don't have to wait for the first person to complete this part. So I guess one way you can do this is that a parallel processing could be instead of having one person do all of like, you know, the grading of one test, you can split up the test into different parts and say, all right, person A, you're going to grade all of these papers, and person B, you're going to grade all of these papers. And at the very end, we'll combine them together. That's kind of more parallel processing. So
sorry, so how is that any different than the top one?
Distributed?
Yeah.
Yeah, so this is the weird part, is that distributed basically means that they're literally different CPUs that are like getting this information. It can be, for example, distributed system where like you wait for one person to do step one and then you pass it on to the next person to do step two, and then they pass it on to the step three and kind of go in that way. Where parallel is much more, you don't have to wait for the next person to finish their first thing and then you'll combine it later.
Okay, I guess I don't understand how that's any different than the server-based one.
Mm-hmm.
If like you just split it up by the steps to each, or are you saying that the server-based one is like you're not sorting it, and steps would be someone considered sorting it?
Yeah,
Or is
it's not.
parallel meaning that like the steps aren't contingent upon the previous step being completed? Sorry, I'm not getting this.
No, it's okay. It's okay. I think it is kind of confusing because so many processes are distributed in parallel together. Usually you're doing this in a way that is both parallel and distributed. So I'm trying to think of one that's purely parallel and one that's purely distributed. Trying to think of a good way to do this. I don't know. I think maybe a good example, just literally looking up like distributed versus parallel, right?
Yeah, that's what I just did.
All right, good. If you find something, then that might be.
Okay, yeah. I'll look into it.
Okay. So yeah, I would kind of check this. Usually you're doing them together, which is kind of confusing because like that's why they're so easily kind of mixing together. So here's a little diagram, right? But basically the difference between these two, like I kind of mentioned, is that distributed system is that you have your own like CPU with the memory. So they can work on things separately, where parallel technically has multiple CPUs working on the same memory itself. So the thing is that you might have parallel computing within a distributed system itself. So yeah, I'll let you kind of chew on that, I guess, maybe.
Yeah, I'll just whatever.
Maybe we'll come back to this then. I don't want to much on it too much, right?
Yeah, don't worry.
But, usually, to be honest, they're mixed together.
Okay.
Okay, cool. So so we kind of talked about distributed, talked about parallel. Usually they're mixed together in some way. But yeah, I'm still trying to think of a good example in the back of my mind, but we'll skip over it. So now it's like actually applying to tools. So one tool, one framework that's really common, that has been common in a while, is called Hadoop. I think it's Hadoop. Yeah, whatever. Basically, literally the story of Hadoop is that like the guy who came up with it, his son used to call his a little elephant Hadoop. And like just basically like he said, oh, that's an interesting name, and kept it for a few years until like he made something and said, oh, I'm going to call it Hadoop since I have a name this stored away, which is kind of weird. But anyway, Hadoop framework is kind of considered old school. It's not bad in this way. It does tend to be slower because essentially what it has to do, it has to write everything to disk eventually. It's based on Java, but basically it's a really like solid platform. I think Facebook still uses Hadoop. They haven't actually migrated to anything faster because it works well enough. But essentially what it is, we have our storage system called Hadoop Distributed File System, HDFS. So you'll see this very commonly, HDFS. We're talking about distributed and parallel processing. There's a data processing called MapReduce, which is super confusing because MapReduce is more like a philosophy, but there is also a programming language called MapReduce. And essentially it's a way to process data in parallel, essentially. And then Hadoop also uses a resource management. So basically you can think of it like the director of saying who does what where. So that way you can do multiple parts and then understand, say, okay, this information is stored in different spots and you can combine them together later on. But that's essentially what the Hadoop framework system is. Essentially is making a distributed system. Okay. But Hadoop is kind of on, like I said, kind of old school. The new stuff right now is Apache Spark. And so Apache Spark is also written in Java. It's a little bit fast. It's faster than Hadoop, or generally is faster than Hadoop because it holds data in memory whenever possible. So it's holding it all within RAM. So it's able to basically crunch numbers a lot quicker and doesn't write it to disk unless it needs to. So you actually get a little bit faster speed on this. What's kind of nice too is it can also be built on top of Hadoop, but can also like HDFS, but also can be built on some newer systems like S3 on AWS. So S3 is kind of like a way of storing information on Amazon Web Services. So that's really useful for the web stuff, is that you can build it on top of things that already exist. Spark has kind of become like the big name in data science because it does a really good job of doing things like ETL, extract, transform, load in machine learning systems. So you can basically do this all within memory itself, and you can do this on a distributed system. Okay. So I would just know that there are two different frameworks, Hadoop and Apache Spark. Like I said, Hadoop is good, but it's definitely older school, but it doesn't mean it's like you can't use it. So just because you kind of have to think of it as what I have here, you can think of what you've been doing so far to test our big data. You can also use PySpark in local mode, no cluster required. Yeah. So basically is that you use the tool that is available to you. Like I said, I believe it's Facebook that actually uses Hadoop still, and they never transferred over to Apache Spark because it's like, well, it works well enough. They don't need to spend all that time to transfer it over. Also, you'll notice if you run Spark with the labs within the curriculum, you'll notice when you run it, it actually runs a little slow. And the reason why is because you're meant to use it more in a distributed system where if you try to do all of this on one computer, even though like something like Pandas can be really quick, you can't actually load all that data in one machine. So you have to use something that's more distributed system where maybe it's a little bit slower, but you're able to process more information because you have many, many instances. Okay, cool. Any questions on that?
No, that makes sense.
Okay, cool. Yeah. So again, we'll mostly focus on Spark and the curriculum itself, but just know that Hadoop exists and you'll probably see it around too. So this leads us into MapReduce, this concept. So again, this is actually taken from the curriculum itself. And so MapReduce, because I mentioned before, computer scientists are really creative in their words. In other words, they're not. Basically, there's two parts in it, map and reduce. And I would actually even say they messed that up because there's actually slightly more than just simply mapping and reducing. But basically, this is kind of like software or a philosophy of approaching that's really good for clusters or distributed systems. So you can kind of imagine is that you might have multiple parts working on something at the same time and then combining it later on. So just kind of walking this through, this is from the curriculum, is that imagine you have this one file that has basically a bunch of like names of animals. So like your lion, tiger, wolf, lion, giraffe, in no particular order. And what you want to do is be able to count, how many times does lion occur, right? Or how many times does koala occur? And so what you can do is like, well, if you had to do this yourself, you could get this one computer and feed it this information and count through it. But if your zoo file is very, very, very large, it might not be able to fit on one computer, and it might take a long time for you to actually process through. So basically what the idea here is we'll take this one big file, we'll split it up, do our processes it, and then combine it later on. So that's essentially what MapReduce does. So there's basically 4 steps in MapReduce here, and I'll repeat it down here as well. But basically it's the splitting part where essentially you take this big file and you split it up into different, basically different CPUs. And then you would map each part out to basically say, okay, get ready to do some calculation onto it. In this case, you can see it splits it up into lion, tiger, wolf, lion, giraffe, giraffe, penguin, and so on. So each computer only sees that little rectangle. And then it maps it out, says, okay, well, there's only one lion that occurs, one tiger that occurs, one wolf that occurs, and so on. So you can see these different parts just being mapped over, okay? So the mapping is kind of like, all right, getting ready to do something. Then what we do, which I think is kind of confusing, it's called shuffle, the shuffle step. But essentially what it is, it's more like reorganization. And so basically everything passes it to say, all right, this first computer is only gonna get giraffe. This next computer is only gonna get koala, and so on.
It's literally the opposite of shuffling.
I know it's super weird. Like computer scientists are like really weird, I guess. Like I don't know who called it shuffle, but I guess in
It's
some
like when
way
you shuffle a deck of cards,
yeah.
you unsort them, and this is whatever.
Don't get me started, right? Like, who came? I I never looked into who came up with this, but I swear I'm just like, there's so many parts. I'm just like, because it looks like it should just be map and reduce, but it's like, oh, you have to split and then map and then shuffle, but it's not shuffling anyway. But yeah, so essentially what you're doing, you're organizing it in some ways. Basically, you're getting all on one computer. So that essentially all they have to do is like, oh, let me just combine all of these together, and this will reduce it, okay, to this one element here, and then you can combine it over at the very end. In this case, koala, lion, tiger. Note sometimes is that in this scenario here, you actually see that giraffe is like in just one instance, but you might actually have giraffe into multiple instances. Or in some cases too, like if there's very large values, if there's only one occurrence of koala, you wouldn't want to use your CPU just to do just koala. You might actually have them do koala, tiger, and wolf on one because it's relatively small. So even though it would technically take more time, it's okay because it's relatively few elements in here. And so the idea here is that you can't tell ahead of time which one's going to finish first, but you know what eventually they'll end up being, and then you can reduce it from there.
Okay. I think I'm seeing, or are you about to go into this?
No, go ahead.
I think I am not really sure how you're going from map to shuffle. So are you like recombining everything back into something else after map and then splitting it up by shuffle and like sorting it? Or are you like, I don't know, running something that would pick out each, yeah.
Yeah, this is where like it's kind of, so remember how I mentioned in Hadoop, there is a resource management system. This is where that resource management system goes and says, all right, computer, let's say this is CPU A, like on this row right here. In resource management system, like the director says, all right, computer A is going to get all of this information over here. Whoever has giraffe, go ahead and give him, you know, giraffe, right? And then he says, okay, computer B is only going to get koalas. Everyone who has koalas, give him koalas. Essentially, it's going to give, I guess that's why maybe it's called shuffle, because it kind of looks like a madhouse because it's happening all at the same time.
Mm-hmm.
But the idea here is that this information, like lion, for example, I'm not going to try to make it too messy, but like lion gets passed over to each part right here. And so someone says, okay,
yeah, I guess I'm just,
Mhm.
yeah, like I'm wondering how they're able to iterate through the information on each separate like instance.
So you're saying like going through that part?
Yeah, because like wouldn't it take some like what is the computation? So for example, for I would say call it computer D, where it's penguin, lion, giraffe, like it would have to like in order to ask if it has wolf, it would have to check is penguin wolf, is lion wolf, is giraffe wolf? No. Like I'm sure that don't all those checks like require some how is it able to like iterate through the information on a separate instance and yeah.
Yeah, and this is where it's a little like we're kind of abstracting part of it out, which is leaving out some details. And basically, to really make it short, it's like it's the resource management system that's actually deciding where the things go ahead of time. In reality, you wouldn't have one director. You have essentially, I'm calling it director because that kind of makes sense. But like the resource management, it's not like one single thing that's telling it what to do. There are multiple copies that are telling each one to do a certain process and stuff. The good thing is that for the most part, you don't do the resource management system. It is mostly used to already be optimized, if that makes sense. This is a simplified kind of version. We can actually maybe see this a little bit better when we actually try running a MapReduce problem. Hopefully that's doesn't feel like I'm sidestepping you too much on like.
No, that's fine.
Yeah. Yeah, and part of it does, like you said, it does take up resources. It does take computation time. It's just the idea is that it'll take computation time, but the hope is that it'll take less computation time to do that than it would have if it had to try to count up all of these parts first. So it turns out these are relatively simple computations versus like trying to count these parts and then combine them later on. So that's kind of like the shorthand of me saying like why this works better. But in other words, a lot of distributed and parallel systems look like it would take a lot longer, like especially distributed, but looks like it should take a lot longer. But the reason why it looks like it takes a lot longer is because we're using very small sets, where in reality, if you had a small set, you would never do this. Like this would definitely take a lot longer process, and which is why when you try doing the same steps in Spark, then in Pandas, a lot of times Pandas will be a lot quicker because it doesn't have to do all this extra resource management. Okay. Does that kind of make sense, Lucy?
Yeah.
Okay, cool. So just kind of review, basically the split part is essentially assigning a task to each worker, and each worker is one of these rectangles, a CPU, right? And then the mapping part is basically taking it's using a function. That's why we use map, like the mathematical term. We're taking a function and taking the data that it gets from the worker and transforming it into another form. So in this case, it's transforming like the word lion into lion1. And the reason why it's doing this is because it's essentially making it easier for it to process it later on in the map and reduce function, or really in the reduce part of the step. And you can think of it as like a key value pair. So if you remember, think like back in dictionaries and stuff like that, reason why dictionaries are actually really efficient is because it basically already knows where all these things exist. And essentially that's more or less what's going on here. It's kind of prepping it to do some more efficient stuff. Last part, like shuffle, it's more like reorganization, like, I don't know, reshuffling, like ordering it. Basically, it's the idea is that we're shuffling it and we're going to make it so it's easier to reduce later on. And then our reduce step basically is combining all this information into smaller sets. So then it can all set it's into smaller sets and it's relatively easy to put together. So you can see here, basically, it's like we can see giraffe 3 is going directly into here, and they don't have to worry too much about the other workers and stuff and what they've already achieved. Okay, so that's like the concept of MapReduce. Cool. Yeah, so I guess we can go into a little example then. Sound good?
Woo!
All right. So MapReduce. So I'm actually not going to use what's it called? Use Spark. I think I like to use MR Job, which I like talking to the other instructor. It sounds like Mr. Job, but MapReduce Job is when it's going.
Okay.
So it's really simple to just install right with pip. But basically, you can see here, I'm running this as if I'm running in the terminal. Is I'm going to have this count right here, song count.py, and this is actually the data songs.txt. So essentially, I'm going to show you what that looks like. And it's a relatively small amount of data. Let's see, songs.txt. So you can see here is that essentially these are all the song names. Okay. And I just took this from another thing, but basically there's just made up stuff. So basically what we want to do is count out how many like times Deep Dreams occurs, how many times Data House Rocks occurs, Broken Networks occurs. And you can see, I don't know how big is this, 2,500-ish, right? So it's not a huge data set, but you get the concept that I think there's like 3 different songs. So the code here is, I'm just using Mr. Job, and just know that you don't have to necessarily use, what's it called? Like similar thing would happen if you use PySpark, but I'm kind of just showing this because it's more like the MapReduce side of this. So essentially we have 2 parts, which is the mapper and the reducer. And essentially what we're going to do here is each line will be read in. So that's what this mapper is going to do, is essentially going to take in each line and transform it into a tuple, a key value pair. So essentially what it's going to do is going to take in this line right here, and it's going to output basically a song name and number 1. And basically that's all it's doing. So you can see it's really, really simple. It's not doing any high level computation at all. And that's kind of what we want. We don't want it to do a whole lot of computation. And you'll notice here this is the yield symbol, which I don't think you've seen yet, right, for Python. Yeah, and so this yield, you can kind of imagine it as just the same thing as a return function. So like, you know, in a function, we can just say return, and it would return that whole thing. A yield is an interesting one because basically it's getting one element at a time. So this mapper will take in essentially all of the song, like the list of songs, and it'll take that all in. And when we do like, you know, call, like say, all right, give me the next one to mapper, like, I'm simplifying this, but basically, hey, give me the next one, and it'll give you just one element in it. And then say, all right, give me the next one after that, and it'll give you another one. So give me a next one, and give me the next one after that. So that way we don't have to keep running the function. Essentially, it's almost like a built-in like for loop. And in reality, like if I'm going a little deeper, this is called, like, if you want to look this up, is actually a really useful term. It's called a generator. So
what?
A generator.
Okay.
And basically, you can think of it as whenever we do for loops, like for example, if you do for I, like if I do right here, for I in range of 10, what this is, of 10, this right here is a generator. And so what this is actually doing, it's saying, all right, you're going to give me a list from 0 to 9. And when I ask for the next one, give me the first one. Okay. And then when I ask you the next one, give me the next one after that. So the first time you ask is like, give me 0. All right, give me the next one. That's going to be 1. Essentially, that's what we're doing right here. We're making our own like range function, essentially.
Yeah, that makes sense. Okay.
All right, awesome. So it helps in saving memory, especially because then you don't have to you don't have to load the whole list of songs into memory and then
Yeah.
proceed. Just like the next one, next one, next one. So once we have our mapper right here, and then notice that there's no split and there's no shuffle functions in here, and that's because that's being taken care of MR Jobs resource management system. So we don't actually have to do
Okay.
that. But you can see the reducer part here is basically saying, okay, we're going to get, this is just the class itself, right? But we have the key and the value, and essentially say, okay, go ahead and for every key, go ahead and sum up these values right here.
Yep.
That will get the total part. And that's, the idea here is like, oh, it's already, the resource management system has already decided which things each worker is going to run, and it's going to just sum up those parts, and it's going to be nice and easy for it to do. Okay, and then it's going to.
Sorry. Does the I'm just how would this output, like, would the yield then output like all the different keys at once? Like, what would the output of reducer look like?
Yeah. So what's gonna?
It would be like three different key because. Oh, actually, no. I think I get it. Yeah, it would be all of the keys and then their relevant sums. I was just wondering if it would just be like one at a time. Since
Yeah.
like when you're calling the range, it's like theoretically it's just spitting out like the first one.
And yeah,
Since
that's
it's not storing all. If you're calling a range of 10, it's not storing 0 through 9. It's just asking. It's like a for loop within itself. So for that function of the, I don't remember what it was called, but for that function for the yield, would it spit out just one at a time, like the first key, second key, third key every single time, or is it spitting out like a 3 or 2 by 3, 3 by 2 data frame or something,
Yeah, it's what it's really doing is that this reducer is going to operate on one worker. And so if I'm going to go back to here, it's essentially when the reducer runs, it's already in this state right here.
Okay.
And basically this value is all of these guys.
Got it. Oh, because the other one's it's already been mapped and shuffled.
That's right. And this is where the reason why we have that too is that it's all right. But you also have like
spitting out one.
Exactly. And the reason why this is like also like, oh, why don't we just use one of them? Well, the resource management system, it's not really shown in here. It might actually have Koala 1 and Tiger 1 right here as well. Yeah. So that might be part of the reason why we actually have a key.
Oh, so you have to, yeah, okay.
But the nice thing is we don't have to worry about it too much. It's kind of like, oh, basically something in the background.
Okay, so in the instance where it was koala and lion or whatever, would it spit out both?
Yeah, it would spit out basically koala and then lion 3.
Got it. Okay.
Cool. Right. Awesome. Yeah, so that kind of I think hopefully that kind of helps things out. But I would quickly just say like about generators is like, for example, if I do a range of like 10, you can see that goes by really quickly. If I do like a range of like, the shouldn't crash my computer. You can see how quickly that went, right? Like, and you're like, whoa, like, man, like, how is it able to do all that? Like, look how quick that is. The reason why is because it hasn't done anything yet. It's just waiting for the next part. So I can do this really quickly versus actually, if I try to convert, I'm not going to learn it right now, but like, if I did lists like this, you'll see it like that little star come up and it'll take a long, long time because now it's actually trying to convert it over to a list. So that's essentially what we're doing. We're kind of cheating the system. We're kind of being lazy about it. Okay. So yeah, so that's the simple part. Basically, I just made this mapper. I made my reducer. Okay. There's going to be some resource management done in the background, and I can actually run this code. So what's nice is that I can basically say, all right, take this code right here, which is a songs.py, and then feed it in that data, and it will go ahead and it should count basically for each line. It's going to count out the different values. So I'll go and run this. And you can see here, basically it figured out, and you can see there's some extra stuff right here, basically talking about management and stuff like this and different streaming. But essentially my results are Deep Dreams, 1,131, and then Data House Rock, and then Broken Networks. So you can see they're just different elements here. And for the most part, that's relatively quick. If I were to copy this over and over and over again, essentially, this is not the best example because it's only being done on one computer. I mean, in this case, I think MR job actually looks at CPUs. So if I have multi-core, I can actually do this multiple times or like have each worker on a multiple core. And so at a certain point, it'll be a certain like speed, but then after that point, it's like, oh, I don't have any more CPUs to give it, so we'll slow down again. But if that was the case for a distributed system, what you can do is just give it to, all right, we'll just spin up new servers and we'll give it new information to pass on. And that's what Spark is essentially doing. Okay. Does that make sense?
Yeah.
Okay, cool. All right. And so that's my simple example here. Next example is, let's say we want to just count how many words there were, right? For Romeo and Juliet. So kind of similar with our zoo file, but let's say we have this text file and you can see here a Romeo and Juliet. This is a little more complicated right now. Right now we're not having this nice, beautiful list. So basically our worker is going to read that one line and we're going to have to go ahead and, well, first of all, it'll be split into different lines, but then we have to reduce it into something meaningful, right? To actually do something with. So you can see here in this case, and I think I fixed this because I had an issue before. Essentially this mapper, right, is going to basically, we're going to have it split up. So basically we have this line and we're going to take that line and we're going to map it off to something. So in this case, we take a line, we strip out basically all of the extra space. I'm actually getting rid of the punctuation as well. So that way we don't have to worry about like, you know, something with a period at the end. And then we'll split up the words into basically a line. So this one line is to split into a list of words. And then for words, we're basically just going to make it lower so it's consistent in this case and just yield off one each time. So in this case, this mapper is going to take one line. Where am I? There it is. This one line and basically make it all lowercase, get rid of punctuation, and basically return, you know, this word, comma one, this word, comma one, this word, comma one. Okay. So that's what this part is. That's the mapper. And then the reducer all it does essentially does the same thing like we did with the song count list thing. Go ahead and take each word and sum it up. And so now, I think I fixed this because I think, also, let's see. Okay, good, so it worked. So you can see here, I ran this whole thing and essentially I counted out each word and you can see here, it's like C occurs 39 times. I didn't take out all the punctuation. So you can see here, this didn't quite work out, but you get the idea, is that it's able to count out each word and how often they occur.
Would this be, could this kind of be like a start to text mining?
Yeah, actually, this could be something where you're taking this data in there and you want to you want to process that data. Where like if you imagine, like you can see, this is the full thing of Romeo and Juliet. Like it's pretty decently sized and that happened relatively quickly. And the reason why it was able to happen relatively quickly in less than 1 second is essentially because it's splitting it up. I think I have, I actually don't know how many cores I have. I'm pretty sure I have at least quad core. So essentially it's splitting up into, well, it's confusing too because there's different threads, but essentially they're different workers and I can split those parts up. But yeah, this could be something for if you want to basically, you can imagine like if you want to text mining, let's say you wanted to pull up each like web page and each worker will work off of that one web page. You could do something like that as well.
Yeah, okay.
And this is where like that word I said workers is an actual term. Like that's not like me making it out. Like again, it's something that
stop personifying the computers.
I know it's kind of funny because like I'll personify, but then I also forget like that's the technical word. So
yeah,
actually like I actually put this before in the resume and it's like, oh well, you were using workers to do this job. I'm like, what are you talking about? I'm like, oh no, I was talking about real workers. Like, so just kind of be aware of that too. Like, you can kind of catch yourself in some weird, it's weird conversations with people sometimes. But anyway, yeah, so that's kind of essentially like, this is not Spark. I want to make that really clear. But the concept of this map reducer is essentially what you can do in Spark as well. But I thought this was a little without any extra Spark madness that we're going to have to deal with. Essentially, this is just the pure map reduce. Okay.
Okay.
Cool.
I didn't know string dot punctuation was a thing.
This guy right here? Oh,
yeah. Yeah. How? I'm trying to see like what, because clearly didn't get all of them.
Yeah, I think I might have messed up on part of it. Let's see if I add a new, oops. Let's add a new part here. So.
Oh, it looks like it has all of them.
Yeah, I think it's the way I did this part. Here. I have to look at this closer. Oh, where is it? Yeah, I'm not sure why this didn't work the way I expected. You know, this is a list of words. So I have to, I messed this up. You have to go through each one of these punctuations and replace them, if that makes sense. So I would have to do something like, oops, that's not gonna work. Well, this is not gonna work regardless because this is
No,
kind
I
of,
see what you're saying though.
yeah, you can see I removed each one depending on what punctuation it is. So there should be at least one. Oh, I guess I didn't do this backslash. There should be like, there we go. So you'll see one of them missing a semicolons, one of them missing this part. But I'd have to basically, this is me not, this wouldn't work by itself. But essentially this is just a list of punctuations.
So it'd be like for all, I'm trying to think how to do this, for all punctuations in the string, replace every punctuation with nothing.
Yeah, I'm pretty sure there's a
Would
better.
you have to iterate by character?
This is like,
Or
yeah.
like, would you be, is there a function that outputs all of the punctuation attached to a string?
Of like a string like to this guy right here?
Yeah.
I don't know specifically. I think, to be quite honest, I think the best way to do this is probably with regex, is probably using regex and say, if there's a function or a punctuation in here, just remove it.
Yeah.
This is not an efficient way. You wouldn't want this, especially considering
Yeah,
that
right, with that many, yeah.
Yeah. But yeah, and you can see it didn't work in this case because it's looking for that whole string of punctuations and replacing that whole string of punctuations in the line, which of course isn't going to work because that doesn't exist.
Yeah, that makes sense.
Mm-hmm. Cool. Anyway, but that concept at least works out.
Yeah. Sorry, I was wondering how I would do it.
Of course. No,
I'm not, oh my God, I'm not picking apart your code.
No. No, that's good that you're thinking about like ways you can make it work. I just wanted to make it clear that like that thing does not work. So
as we found out.
Yeah. And you see, if you look at it too, I put a note. Where did I put it? Oh, I deleted it by accident. But let's see here. Yeah, you can see here, to do word count needs some fixes before it works properly, punctuations. Because I tried this, I'm like, oh, wait. So again, if you took more time, you would be able to get rid of these punctuations. And that way, price and price is like a count twice. Okay, cool. All right, well, that kind of ends everything I had to say about for distributed and parallel systems. So, do you have any other questions, Lucy? Then?
No, I think that all makes sense.
Okay, cool. All right, so I'll go ahead and stop the recording here then.